Welcome, oh welcome. My name is Cenk, and thanks for joining this Christmas tale on how to secure the Web of Things with content object security. My audience is actually quite small, at least this room, but we have really tasty cookies here. I think there are much more people in the video camera. So let's let's begin the merry story with the internet, the network of networks that provides global connectivity and enables a couple of very useful and very important use cases. Children communicate wish lists to Santa Claus, and Santa Claus commands his Christmas elves, or in some other countries, more prominent in the former Soviet countries, he commands Snegurochka. Does anyone know what that means or who that is? No? Maybe someone from the camera? From the Zoom call, does someone know who Snegurochka is? No, okay. No, so I mean, in these countries, actually, the Santa Claus is called Grandfather Frost, and Snegurochka is his granddaughter who helps him with carrying out the presents. Another use case is that Santa catalogs children, and elf data analysts analyze wish lists. We have elves that play Candy Crush during preparations, and Rudolph plays Fortnite to relieve stress. And then there's the web shop. Santa orders toys from specialist retail stores, and parents browse Santa's web shop to buy the presents. So there's this problem. History shows that the internet is a dangerous neighborhood. We have eavesdropping, we have tampering, we have message forgery, and as you can see, you can even lose a leg. But there's a solution, and that's actually, let's say, the solution actually dates back to 1987, and this is transport layer security, where two endpoints are secured in such a manner that messages cannot be read from nodes in between. All right, the IoT. Santa loves IoT. He is using IoT to measure the moisture beneath his head. He's controlling his smart hut, and he's managing the temperature for his snowman friend. And of course, he's measuring the blood pressure of Rudolph while he plays Fortnite. And the typical IoT deployment looks like this. We have constrained IoT devices, we have a gateway, and we have cloud service on the other side. And usually on the side between cloud and gateway, we use HTTP atop of TCP for the communication. And on the IoT side, we have the at least co-op envisioned, the ITF envisioned co-op network stack application layer protocol, which is co-op, which runs on top of UDP. And to make the IoT setup secure or protected, we use transport layer security, which is HTTP over TLS for the gateway to cloud side, and DTLS for the constrained device to gateway side. All right, so the IoT is protected. Is there anything more to say? So I hear a voice. That is the cookie man who's speaking up, not so fast. Let's have a look at the transport layer security for the IoT first. So DTLS for CoAP, so it operates on UDP, like I said previously, and it follows the TLS specification very close. It prevents eavesdropping, tampering, message forgery like TLS, and it uses, like TLS, the 5-tuple endpoint identification, which is the IP port source, the IP port destination, and the transport protocol identifier. There are two layers that DTLS provides, like TLS. We have the Handshake Layer. The Handshake Layer is used to establish a session between two endpoints. And then we have the Record Layer, which is used to encrypt and decrypt all packets that go through the layer. So in this case, we have an example. The client sends a message, call me Ishmael, which is the very first words of the Moby Dick novel. And it's received by the server, and any node in between can decrypt that. There are, however, a few challenges for these kind of setups. And one of those is protocol conversion. Like I showed you the picture before, we have gateways that speak TLS to the cloud and that speak DTLS to the IoT devices. So specifically these devices, these gateways, have two security endpoints, which means that messages between these endpoints inside the gateway are unprotected. So there's actually no end-to-end security that reaches from a sensor node to the cloud. And then in the IoT, we have devices that can come and go. It's quite dynamic structure. And as soon as you change one of the variables of the 5-tuple, then we need to establish a new DTLS session, which is very costly and power extensive. So now let's look at the content object security for IoT using CoAP. OSCORE is object security for constrained RESTful environments. It's a proposed standard since July 2019, and it builds on COSI, which is CBOR object signing and encryption. OSCORE provides the security properties confidentiality and integrity, which it inherits from COSI, and it also adds replay mitigations for CoAP messages. So let's first look at COSI very quick, because I talked about COSI so much. COSI gives you a recipe on how to organize data in a memory map, and then defines cryptographic operations that you can use on these information. COSI is using CBOR, which is the JSON equivalent for the IoT, and COSI builds and improves on Jose, or at least, I mean, it's probably pronounced Josie. I'm not really sure how to pronounce it. But COSI defines at first a header message or a header format. You have parameters like algorithmic identifiers, key identifiers, the content format of the payload, or initialization vectors, and other stuff that are used for the cryptographic operations. And using this header, we have, I only show you 3, but there are actually a little bit more of those further expanded constructs. So we have COSI MAC0, which is using the header structure, and then it's you can input the payload, and then it generates a message authentication code for that payload using the header. We have COSI Sign1, which is very similar to COSI MAC0. You have a header, you have the payload that you input, and then you get a signature for that payload. And you have COSI Encrypt0, which uses, again, the header structure, and you input the payload, and you have then the ciphertext, the encrypted payload. And now we can understand what actually OSCORE is. Imagine an unprotected CoAP packet. We have the header of the CoAP packet. In this case, the method code is put. It could be anything else. We have the flags of the header. CoAP options are present. It could be the URI path, the content format of the payload. It could be proxy URI option. And then we have the payload. In this example, again, call me Ishmael. And then we have OSCORE context. And that's now new to the whole setup. OSCORE context contains the key material and further information that is used by OSCORE. Then we take the COSI Encrypt0 that we saw on the slide, in the previous slide. We put the OSCORE context inside the headers, so we initialize it with the algorithmic identifier, the key identifier, and further on. And we also put information into the ciphertext. We put the header, some options, not all options, only a few options, into the ciphertext and the payload. Then we generate and encrypt all the information, and then create a new packet, which is a protected CoAP packet. We have a new header for the CoAP packet. In this case, it has to be method code post. That's how it's defined. We have a new option, and this option is now an OSCORE option. And that OSCORE option includes the header part of the COSI Encrypt0. And then we have the payload, and the payload is the ciphertext of the Encrypt0. There's also another contender that provides object security for the IoT, and this is named data networking. So named data networking is a proposed future internet architecture. It actually is around since 2006, but back then it was content-centric networking, CCN. It follows the information-centric networking paradigm, and it is situated at the network layer, so it replaces IP. The key aspects of NDN are that it's pull-driven. We have request messages and we have response messages. There's no way of pushing unsolicited data. There are no endpoint addresses. So not the hosts are addressed, but the content is addressed. And we have routable content names. In the forwarding information base, we use content names. Each node along a path is using a cache, so we have network caching, the hopwise network caching, and NDN supports an inherent multicast support, and of course provides content object security. And research indicates that NDN actually promotes the resiliency in IoT deployments, very constrained IoT deployments. So let's look at some numbers that we collected during our last papers. We look at this protocol ensemble. We have co-op over DTLS, we have co-op with OSCORE, and we have NDN. The testbed setup, at least for this paper that you can see down here, Networking 20, we used the IoT Lab testbed, which has like IoT hardware, and 15.4 radio is frequency standard. So we have used the software platform Riot with TinyDTLS for the TLS part, libOSCORE for the OSCORE part, and CCN Lite for the NDN part. The topology is as depicted. We have signal topology with 10 sensor nodes, a gateway. We have the multi-hop topology that extends these 10 sensor nodes with 5 forwarders. And we have this scenario where the gateway requests content every 2 seconds from each sensor node. Let's first look at how the completion time, how we measure the completion time. So we send a request and receive a response, and the difference is the completion time. That's what you can see on the x-axis of this plot. On the y-axis, you see the cumulative distribution, and then we show these plots for co-op without protection. Then we show it for co-op DTLS, co-op with OSCORE, and then NDN without protection and NDN with protection. Let's look at the single op case first. So, okay, here we can see that almost all requests and response, the completion times are below 1 second. If we zoom in, then we can see that there are like small differences between the protocols, which is mostly due to different packet sizes and protocol operations. But what we can see is that, of course, the protected versions of the protocols complete a little bit slower than the unprotected versions, which is due to the added cryptographic operations and the smaller added overhead of the packets. Then if you look at the multi-hop setup, which is the more delicate setup, then we can see these staircase patterns. Staircase patterns in this context means that we have retransmissions. So if we lose a packet, then these protocols all do transport layer for co-op or hop-by-hop retransmissions for NDN. Every 2 seconds. That's why we see a staircase at the 2 second marks. If you look at co-op, the normal co-op DTLS and co-op OSCORE, we can see they perform mostly similar. If you look at NDN, then we can see that for the first 2 seconds that we lose a little bit more packets than for the with the co-op deployment because of a difference in the packet sizes. NDN actually has larger data packets. But we see that NDN is able, after a certain time, to recover lost packets using hop-by-hop retransmissions, so that it actually achieves, if you look at the 10-second mark, a very high success rate of completed requests. So what we saw is that hopwise content caching of NDN increases the reliability of the setup. Let's now look at the request creation time. So the gateway creates the message, the request, and this is how it looks like. Co-op has, we see on the y-axis, it's microseconds, so it's actually really fast. Co-op has like almost 200 microseconds for creating the request, and we can see it only increases if we add more protocol features, so the DTLS and OSCORE. And NDN unprotected is kind of slow. It's still microseconds, so everything is very fast here. But this is more due to how the protocol is handled, and we have different protocol, the packet structures are much more different, which leads to these numbers. But the interesting part is now if you look at only the retransmissions, because retransmissions actually exist for co-op in the co-op layer, they are already done, and we only need to copy them from the buffer and resend them out. And you can see for co-op and for OSCORE that the time is very similar. It's very low. It's just a copy from the memory to the layer down. But for co-op with DTLS, we see much more. Yeah, the creation time is much higher, and this is because of the layering. So we saw DTLS is below co-op, which means that every co-op message has to traverse the record layer again, and we need to again do all the encryption to send the packet out. And this is why DTLS record layer generates a higher load on retransmissions. So from these experiments, we can take away that OSCORE brings a lean object security to constrained IoT. And if you look at the paper that I mentioned before, you can also see that OSCORE, because of the better integration into co-op and reusing certain co-op features, it exhibits much less overhead in terms of packet bytes. Co-op DTLS shows more overhead when the endpoint changes, so when the 5-tuple changes, or on retransmissions even. And NDN has a higher reliability due to the hopwise caching feature. And that's actually the feature, the property that leads us to further elaborations. So there are the benefits of information-centric networking, properties for the IoT that was shown in like different research articles. So the stateful forwarding and caching property shorten the request paths and reduce link traversals, especially on retransmissions. And content object security enables an end-to-end security that, well, without handling the sessions actually, especially if we lose the packets. So you can see more, well, information on that if you go through this paper, to our ICN20 paper, but I will outline this here very quickly or briefly. We wanted to see, can we build a co-app that is very similar to NDN and or adopts all the properties, the benefits of NDN. And we looked at all the features that co-op actually gives you. We looked at the communication model and flow control first. The co-op get method is actually very similar to the NDN way of doing content retrieval. So we have a request and a response. And we have acknowledgements and retransmissions for co-op, very similar to what we have in NDN. If you look at the stateful forwarding and caching, what NDN provides, there is this property or this functionality called co-op proxies in the standard RFC, and co-op proxies actually do a kind of stateful forwarding. So they receive requests, they send out requests to another way, and return and responses go back the same path the requests came in, and that's very similar to what NDN is doing. And proxies can perform response caching, also very similar to what NDN can do. And then we have, of course, OSCORE, what we talked about. So we have an end-to-end security that goes beyond protocol conversions. And with these features, we try to figure out, okay, now we have all these features, what can we do with that? How can we build the NDN, an NDN-like deployment to gain all the benefits? And this is what we did. We have a multi-op path, or we have a deployment. And each forwarding node on this deployment is using or is a co-op proxy. So this means we have stateful forwarding on each hop. We have a caching on each hop, and all messages are OSCORE protected. And since we are using co-op on the application layer, we have names. So this is also very similar to what NDN provides. We don't address hosts, we are now using names to retrieve data. And all the things all the ICM properties that NDN is doing on the network layer, we are now doing on the application layer with the setup. And here's a bonus thing that we saw while doing the experiments. Since we are using 6LoWPAN, which is a compression layer for IPv6, we can compress IPv6 addresses from the IPv6 header using this topology or this setup, because 6LoWPAN actually removes the link local, or we can use link local IPv6 addresses in this deployment because we only address the next hop. And the addressing, the forwarding is not really important much further away beyond the next hop because of the stateful forwarding. And using this trick, 6open automatically removes the IPv6 addresses from the 6open header, which is, well, we can say more or less say 32 bytes in the packet for the IP source and IP destination. So in the end, we have smaller packets. Now we measured this setup again using a slightly different topology this time in this paper. Actually, it's a bigger topology, but we measured again the completion time as before using Ndn CoAP, the normal CoAP, and then the CoAP proxy, which I just showed you. We first do this without security measures, so without DTLS, without OSCORE and without Ndn protected features. What we can see that, again, the same staircase pattern as before, Ndn loses some packets but is able to recover most of the packets until it receives almost 100% success rate. Then we look at CoAP, which has a little bit more loss, but is not able to recover as much as Ndn in this case through end-to-end retransmissions. And now using CoAP proxy, which is again hop-by-hop caching, hop-by-hop retransmission features. So like Ndn, we can see that this is enough to receive very similar properties like the Data-deployment. If you look at the setup with security features, so we are using now Ndn with protection mechanisms, and we are using CoAP with OSCORE, we can see that it behaves actually very similar as before without features, but everything is a little bit, of course, due to the added operations, a little bit more worse. But the takeaway is that the CoAP proxy deployment is as reliable as Ndn. Now, we saw what we displayed, or yeah, we saw all the features that we now looked into in the papers, and the takeaways of these features of the papers are that the Web of Things using information-centric properties can be built using only RFC-compliant CoAP features, the proxy, the caches, the communication flow, the GET methods. And this stateful forwarding and hopwise caching improves reliability for CoAP. And this is now a topic that actually touches more the Ndn world than the CoAP world. Since we have a deployment that is very similar to Ndn, we could actually leverage that by now trying to deploy features that are only used for Ndn in real IoT world scenarios, because there are much more CoAP deployments than Ndn deployments. And now we can take, for example, caching strategies or forwarding strategies from Ndn and deploy that in typical IoT deployments that use CoAP. And currently we are looking into the multicast functionality. So, like I said before, Ndn has this inherent multicast support, and we are trying to see if this also behaves like that for the CoAP proxy deployments and what we can gain from that. And this is now the talk. I'm not sure if I rushed through it or if I was too fast. I mean, at least there were no questions, which is, it can be either be very good or either be very bad.
So thanks very much. Yeah, and time for questions.
There's one question behind.
Yeah, implementation-wise,
we can try.
Implementation-wise. It's fine. I think it's fine. Thanks. So implementation-wise, could you reuse code between the CoAP proxy and the ICN caches, or are these like completely decoupled implementations anyway?
I mean, of course, there are decoupled implementations anyway, because it's a completely different packet structure that is cached. What you may reuse are strategies. So if you, for example, if you take the least recently used strategy and you implement it independent of packet structures and
for your specific case, the paper measurements, you had completely independent implementations.
Yeah. I mean, we used the least recently used for both, but this was typically or independently implemented for co-op and for NDN.
Because you already used another implementation. Otherwise, it's just a key value store, right? For name to
Yeah.
bytes.
Yeah.
Okay.
Are there more questions, maybe from the Zoom call?
Nothing on the chat.
Looking, I don't see any at the moment.
Yeah, it's probably not really important for this talk, but the thing I'm always wondering is like, how do you do the hop by hop routing? I mean, do you pre-configure neighbors for every host so you have a topology? Because it might just happen that the next node hears your request.
Yeah, I mean, that's a very good point. This was actually brought up a couple of times also during the the conference.
Okay.
I mean, in this case, of course, we had statically configured, let's say, forwarding information based on the application layer in co-op, right?
So you just tell them your next node
Yes,
is,
yes, yes.
I don't know, they don't name the next one.
Yes, but I mean, this is actually a really good point, and I'm not sure if there's actually solutions for like dynamically finding other proxies that can tell you if there's like other service endpoints or not. One way that could maybe work is using the co-op resource directory to
Okay.
find other nodes that also announce what kind of features they have and endpoints. But I still need to look into this, and I don't know if that
Okay.
works or not.
And the second question, coming back to your earlier example, right? You had this whole, we have the UDP TCP thing problem, and we have to kind of re-encrypt our packets. And the solution now could be we just encrypt them once, because we know we can then send them from one endpoint through the gateway to different endpoint. Would that mean that you have co-op over TLS, or would you then send them as TCP payloads, or how does this work with the proxy?
Yeah. I mean, there are like two ways in doing this. In the first way, don't know if you can see it, but probably not from the camera. Of course, OSCORE is on the IoT side. You have the sensor node into the gateway, which is like co-op OSCORE protected. You could also use DTLS in addition to OSCORE, but it's added overhead.
I mean, for our case, it would be enough if we have object encryption, right? We don't need to put DTLS into that.
Yeah, I mean, also it depends on the use case, but I don't think that you need it.
Okay.
But yeah, and on the other hand, if you go to the cloud, there are certain ways described in the specification where you can convert an OSCORE message to an HTTP message that has
Why
the
it is
OSCORE
encrypted?
block. Excuse me?
Why it is encrypted?
Yeah, you have like a binary block. That's what the HTTP server sees.
Okay.
And then of course you need like an OSCORE plugin or something else in the web server that is able to decrypt that.
I mean, that you know your setup, right? So you could set that up, but that would give you transparent encryption between co-op, OSCORE on one side and HTTPS on the other side.
Yeah.
Okay. Cool. And for the NDN case, would you imagine that it's NDN from end to end, or would you also have a gateway that translates from NDN to HTTP?
Yeah, I mean that's more tricky because usually if you look at between gateway and the cloud, it's basically the internet, right? And we don't have NDN in the internet, so you would.
That's why I'm asking.
Yeah, I mean you could of course use an overlay, so you could have NDN on top of IP,
Mhm.
which could work, or you have to do some custom transformations that protocol conversions that convert NDN requests to some other format. Could be, there are some converters that convert to mqtt, for example,
Mhm.
or you could also use HTTP for that.
I mean, setting up just a VPN or something that transparently tunnels between your endpoint and your server.
Yeah, some form of some overlay form.
Good.
There's a question or two from Martin. So, thank you for the presentation. First, you used single hop and multi-hop setups. Do your results change if you have multi-path setups? I think slide 33.
Yeah. So yeah, Martin, thanks for the question. So at least on this slide 34, there's only one path. You're correct. It's not multi-path. I didn't show you the topology for this plot here, but I told you that it's a more complex topology. And here actually we had multiple sensors that are like distributed along a multipath dodec, so along a tree that connects to one gateway, but there are much more paths.
But a tree would not have.
I mean, it's still a single. Okay, it's still a single path.
But it need not be, right? I mean, you
It
could
need not
also
be.
you could have a routing that actually is sort of how do we say hierarchical routing, where you each step in the DODAC or each step in the name hierarchy is actually reduced by the next hop to the gateway, so that is not needed.
It would still be interesting because then packets like race over different paths to the topology. If you broadcast your request over multiple paths, then you kind of.
Well, depends on what you want to route. I mean, if you route point to point and point to multipoint, it may be more difficult. But if you just go to the gateway and maybe back, that should be easier. Because the point is you want to avoid loops, right? You want to have somehow a path that approaches the destination hop by hop.
Yeah. If you keep a hierarchy in your tree, then it should be easy.
You can. I mean, it depends on how you do it. You can do. I mean, if you use names, a structured namespace, you could like something like have a name extension scheme, and if you use something similar to Ripple, then you have actually how do you call this a rank? Yeah, you have a rank in Ripple, and you know, okay, my next one will have a rank which is below mine. That means I'm closer to the gateway.
Yeah, makes sense.
So the second question, I think I will add my question to this one.
Okay.
The question is, do you think COA proxy will be rather used in Ndn deployments? Who uses what? And my question is, from my understanding, your work is a bridge between like two working groups or working efforts by the IETF, and then you propose your work to both of them, or at least to one of them, IRTF and core, probably.
Yeah, I mean.
Maybe add a note like how these different communities reacted to these results.
Yeah, that's a good point. I mean, the second question first. I mean, your question first. Simpler. So
I thought you could answer all in one.
I mean, yes. So of course, presented all these things that we gained. I mean, the knowledge that we gained from looking at CoAP in the paper. So the ICN community is aware, and we also work together with the ICN research group at the IRTF and presented this there. But we will of course continue spreading the knowledge that we gain from here. On the CoAP side, we have a co-author that is actually quite active in the core working group. So the guys who make CoAP, and he's also trying to bring knowledge that he gained from working with us in the CoAP world. So, for example, caching OSCORE objects is actually not that easy because of a very strong binding between request and response. But the changes he's now doing allows that, and this is something we obviously
changes implementation-wise or standardization-wise?
Protocol standard, yeah. He changes the protocol or extends the protocol to allow that, to allow caching objects.
I mean, this is all very new, so it's very much in flux. So the whole world in the IETF is just emerging. So it's actually a good point to interfere between these worlds because it gives a transfer of ideas.
Can you repeat the first question?
Yeah. So do you think COA proxy will be rather used in Ndn deployments? Who uses what?
Used in Ndn deployments. Sorry. I mean, yeah, of course.
Rather used than
sorry.
So Martin asked about the deployment.
Yeah. I mean, of course. That's also a good point. I mean, it's a fact, there are more CoAP deployments than Ndn deployments. I mean, Ndn is a rather small niche if you look at the IP side compared to IP. So there are already a lot of CoAP deployments, and I think it's much easier to use features from the Ndn part, which did a lot of research work in content caching and forwarding strategies. And it's much simpler to take these and probably put them into the CoAP deployments. There are also some features in the co-op world that are not existent in the NDN world. For example, co-op has this e-tag functionality, which is also used by HTTP. So you can revalidate content from an upstream node without sending the content down. So you can just create a hash and just ask if the hash is still valid instead of, and then the producer just says yes or no instead of providing the whole content again. And this is a complete missing feature in NDN. I'm not yet sure if this is possible to move it to the NDN world, but I will try definitely.
So there's another remark by Matthias saying, but there's even more MQTT deployment. What do you say to this? How can we get MQTT out of the way?
Yeah. Yeah, I mean, that's of course a dispute. I mean, MQTT is not IETF, which does not mean that it's bad, of course. It's still a standard. I think it's...
It uses TCP by default.
It's Oasis standard.
Oasis, yeah. It's an Oasis standard. Yes, MQTT uses TCP, but there's also MQTT SN, which runs on top of UDP, and then you have converters to TCP.
Okay. How does MQTT deal with encryption?
I have to look that up, but I mean, you can encrypt the data you push. I mean,
you can always do that. You can always do some additional
You
encryption.
can also use TLS or DTLS. I mean, it uses TCP or UDP.
If they can translate between UDP and TCP, they would have to decrypt it on the way. That's why I'm asking. Because
I'm not sure they actually care about this in the moment, because MQTT SN and MQTT are not bit compatible. The MQTT layer is incompatible.
okay, so providing end-to-end encryption between the IoT world and the cloud might actually be an argument towards like the stuff you do.
towards using co-op and
Because
or
MQTT simply
yeah.
cannot easily write this.
I mean, MQTT it has maybe a larger deployment than co-op because it's there for a longer time than co-op. But I mean, at least my feeling is that this will change pretty soon. A lot of cloud services adopted co-op now or use co-op in their products and their solutions they provide. I think one is not. I think Amazon is still using co-op MQTT only, but I'm pretty sure this will change.
I think I also read like lots of tutorials that use MQTT. If you have like this IoT tutorial in your local, magazine, then it's often you're doing this with MQTT and you have Raspberry Pi and just TCP. Right? So that change is actually offered in things.
I would like to come back to Marcin's discussion because the question whether co-op or NDN is used more is actually only the deployment of the protocol encoding. But the more interesting thing is, I believe, is that you what you actually do on the like conceptual level, because I mean you can encode many protocol operations in many ways, and co-op does it differently from NDN. But at the end, if we look at all this research time in the information-centric networking, it's more important to see whether there's actually an intellectual gain that actually made it into the real world, no matter whether co-op is the protocol encoding or something else. Could be even MQTT if there is a way to do this with MQTT. I mean, who cares?
Yeah.
It's only bits on the wire.
Yeah. What I also wanted to highlight before, relating to these topics also that, as we can see on this slide 31, that NDN, at least until the network layer, there are much less components included in having all these features. If you look at the right stack, then we have full stack up until co-op using OSCORE. So there are much more like parts in the network stack, which of course, then you have of course more ROM needs, more RAM needs, and the network stack at all is a little bit, of course, bigger than if you compare to the lightweight NDN stack, which might steer the direction to NDN, which could shift it to that the NDN deployments get to it.
I can imagine that it depends more on the implementations and if they are easy to use.
Yeah, sure.
But, like if you have the best Ndn implementation, but the interface sucks, no one will use it.
Yeah, I mean that's of course a true statement.
So,
Yeah.
yeah. I can imagine it's good that if it comes out, if there are libraries, they just offer encryption as part of it, so you don't have the choice like, do I want this? Do I have to look into this, how it works, or can I just use it and the default is just secure?
Yeah. So there are more questions in the chat or in the room?
In the chat, I don't see any new question.
Should we do a collective cookie eating session?
Yeah, now we can actually eat very tasty cookies.
Where do they come
Maybe Jen can show some of them into the camera. Here's the master of the cookies.
I mean, to come back to Raphael's questions, where do they come from? I think they were baked with love from Matthias.
Yeah.
Can you see them?
Yeah, sure.
So he probably has some.
Not with love.
Not with love.
Okay. So that's. Okay. Yeah, there's no more discussion. I see a lot of smileys and similar things here on the in the list. Yeah, then we thank Cenk again. So I'm really happy that we managed to have at least a nice Christmas talk in these complex situations. And now we are getting cookies.
Yep.
Bye bye.
All right. See you guys. Bye bye.
Bye.
Bye bye.